So, in the last lecture, we were discussing heat and mass transfer correlations for the flow through conduits, flow through a pipe, and for the flow around a particle. So, I told you that these correlations depend upon two factors, or at least on two important factors. The first is the flow regime, okay, whether the flow is in the laminar regime or in the turbulent regime. And this depends upon the dimensionless parameter called the Reynolds number, which is the ratio of inertial and viscous stresses. In the flow through a pipe, the transition is rather abrupt or discontinuous. At a Reynolds number of about 2100, there is a transition from a smooth laminar flow with smooth streamlines and no cross stream velocity fluctuations to a turbulent flow, where there are intense turbulent velocity fluctuations in all three directions, though the flow velocity is on average along the axis. In the flow through a particle, we saw there is a sequence of different flow patterns, starting with a symmetric flow pattern at very low Reynolds numbers, to an asymmetric flow pattern due to inertia, to the formation of a separation bubble on the rear side, a wake, the vortex shedding, and so on. So, the correlations depend upon all of these things for mass transfer and heat transfer. The second thing that it depends upon is the surface conditions, whether there is a no slip condition at the surface. That is the velocity of the fluid at the surface required to be equal to the velocity of the surface itself. That is a no slip condition. That happens when you have flows past particles or flows past solid surfaces, as we saw here in the flow past a flat film, flow of a liquid film for past a flat surface, where you have a liquid solid interface, and in that case the velocity is equal to 0. In contrast, for the flow through around gas bubbles, for example, the velocity does not have to be 0 at the surface. There is a slip at the surface because the gas inside the gas bubble can have a non-zero velocity. Okay, so, the gas velocity along the surface does not have to be 0. The gas velocity perpendicular to the surface has to be 0 because there is no penetration at the surface. A 0 shear stress condition is applicable at a liquid gas interface, where the shear stress along the surface has to be equal to 0 because the viscosity of the gas is very much smaller than the viscosity of the liquid. So, these were the conditions that determine what correlations are to be used in different situations. We had first examined the correlations for the flow past flow in a pipe and the flow past a particle in different configurations. Low Peclet number. The Peclet number is small, convection is small compared to diffusion. The convective velocity does not matter. Therefore, the Nusselt and Sherwood numbers cannot depend upon the velocity, they cannot depend upon the Peclet number or the Reynolds number, they have to be constants. That constant is 2 for a spherical particle, okay, and we had seen some consequences of that. The time for diffusion just from dimensional analysis scales as d square divided by the diffusion coefficient. The low Peclet number regime is not of importance in pipe flows, because when for the flow through a pipe, the time for diffusion across the cross section is d square by alpha, and when the Peclet number is small, this time scale is much smaller than the time it takes for the fluid to travel a distance equal to the diameter of the pipe. So, therefore, the temperature, all of the heat transfer happens and the temperature equalizes within the time it takes for the fluid to travel one particle diameter, and there is no advantage to having a long pipe in this case. So, this is not of relevance in pipe flows. High Peclet number and low Reynolds number. Okay. Peclet number is ratio of mass, heat, convection and diffusion. Reynolds number is ratio of momentum, convection and diffusion. So, you can have high Peclet number and low Reynolds number simultaneously only if the ratio of momentum diffusion coefficient and thermal diffusion coefficient, or momentum diffusion coefficient and mass diffusion coefficient, is large. In that case, you have a laminar flow. However, the diffusion is the mass transport is dominated by convection everywhere except close to the surface, where diffusion has to necessarily take place because transport perpendicular to the surface cannot take place due to convection. There is no velocity perpendicular to the surface. And for rigid surfaces, I told you that the Nusselt and Sherwood numbers have to be proportional to Peclet number to the 1/3 power, okay, in this case. And high Reynolds and high Peclet number, for laminar flow in a pipe, once again it has to be proportional to the Peclet number itself. For turbulent flow in a pipe, you have a dependence on Reynolds and Peclet number simultaneously, okay, because at high Reynolds number, the flow pattern changes as the Reynolds number changes, okay. In contrast, at low Reynolds number or for laminar flows, the flow profile is the same. Even though the maximum velocity changes, the shape of the velocity profile is the same, and because of that, the heat or mass transfer at high Peclet number is the convective part of that is determined from the maximum or the average velocity alone. So, in those cases it depends only on Peclet number, high Peclet number and low Reynolds number. At high Peclet number and high Reynolds number, it depends explicitly on the Peclet number and the Reynolds number, okay. And we had looked at some of these correlations for the flow in a pipe, okay. Laminar flow 1.86 P power 1/3, that 1/3 power I told you is because there is a no slip condition at the surface, d by L power 1/3 and mu by mu w power 0.14 if there is a difference in the viscosity between the wall and the bulk of the fluid because the temperatures are different. For a turbulent flow, 0.023 Re power 0.18, the Prandtl number power 1/3 and d by L power 1/3, and then the ratio of viscosities as well, okay. And we had seen how to do some calculations for this particular case. We had to find out what the Reynolds number is and use the appropriate correlations for that particular Reynolds number, whether it is in the laminar or the turbulent flow, to calculate what is the Nusselt number or Sherwood number, and from that the transport rates of heat or mass. Okay. Flow past a flat plate, once again you have a Re power half times PR power 1/3, where Re power half, the Reynolds number is based upon the length of the flat plate, okay, because the area projected perpendicular to the flow is negligible in this case, okay, and similar relations for the turbulent flow. And we had also looked at correlations for flow around a particle. These are usually written in terms of the difference between the Nusselt number and 2. For a spherical particle, the Nusselt number is 2 for low Reynolds number flows, for low Peclet number where diffusion is dominant. So, usually correlations are written for the difference between the Nusselt number and its value at 0 Peclet number, okay, in the absence of diffusion. If you look at the high Peclet number, low Reynolds number limit, you can actually derive a correlation which once again is the Peclet number to the 1/3 power, okay, it does not depend on the Reynolds number. But in a uniform approximation for this, okay, in the over a range of Reynolds and Prandtl numbers are these Rans-Marshall and the Whittaker correlations. And I had also given you some examples of how these are used, okay. So, we have considered so far the flow past rigid surfaces, okay. What about the flow past mobile surfaces? Okay. The basic difference between a rigid surface and a mobile surface, if I take for example the flow past of particle, okay, and the flow past a bubble. Okay. The basic difference is that for the flow past a particle, the velocity of the fluid relative to the particle has to decrease to 0 at the surface, because there is a no slip condition. For the flow past a bubble, the velocity does not have to decrease to 0, there is a finite velocity at the surface itself. Therefore, the strength of convection along the surface has to decrease to 0 at the surface of a particle. It is non-zero at the surface of a bubble. Okay, that is the fundamental difference between the flow past a particle and the flow past a bubble. And because of this, generally for the flow past a particle, the Nusselt number will be proportional to Peclet number power 1 by 3, whereas here is proportional to Peclet number power 1 by 2, okay, times some function of Reynolds number. This function is a constant if you are in the low Reynolds number regime. If you are in the high Reynolds number regime, then there is a non-zero value, there is a non-trivial dependence of this function on the Reynolds number. Okay. So, let us examine correlations for some specific cases. Okay. If I have the flow down a surface, for example, I have a film thickness of thickness h flowing down the surface with an average velocity v average. Okay. And if I look close to this surface, okay, if I look close to this surface, then I have this interface and I have a velocity that is moving, a flow that is moving with a non-zero velocity at the surface. And then there is diffusion of, let us say, a gas into the surface. There is diffusion perpendicular to the surface due to molecular diffusion. Okay. There is transport perpendicular to the surface due to molecular diffusion, and then there is convection which sweeps the material downstream with a non-zero velocity at the surface. Okay. The flow past a pipe, for example, the convection velocity was 0 at the surface and it decreased linearly from the surface. In this case, the convection velocity is non-zero from the surface. Okay. So, if I have a film of length L, okay, a length over which the film is in contact with the gas, okay, over this length L, this film is in contact with the gas, the film thickness is h, okay, then the correlation for the Nusselt number that you can derive, okay, is, okay, Nusselt number is equal to 1.38 Peclet number per half times h by L per half, okay, where the Nusselt number is equal to QAV by K delta T by H. Okay. Okay, this is for a temperature profile, thermal diffusion, where delta T is the difference between the film temperature and the temperature far away. Okay. Alternatively, if I were to write this in terms of the Sherwood number for some species that is dissolving in the gas, this would be JAV by K delta C by H, where delta C is the difference between the concentration at the surface and the concentration in the bulk, okay, C naught in the bulk. Okay. So, delta C will be the difference between the surface concentration, which is the concentration that is in equilibrium with the gas, and the concentration in the bulk. Similarly, temperature will be the difference between the temperature in the gas at the surface and the temperature in the bulk of the liquid. So, that is the definition of the Nusselt number, okay. And the Peclet number in this case is equal to VAV H by D or VAV H by alpha. Okay. So, it goes as Peclet number to the half power in this case. Okay. Okay. So, that is for the diffusion into a falling film. Okay. So, that is for the diffusion into a falling film, and for the diffusion around a gas bubble, for example, of diameter d. Okay, for the diffusion around a gas bubble of diameter d, which is convecting with some velocity, okay, in which the free stream velocity of the fluid relative to the gas bubble is Vfs. Okay. The correlation depends upon the Reynolds number. If you recall, I told you that for a gas bubble at low Reynolds number, okay, you have symmetric streamlines around it. Okay. You have symmetric streamlines around the gas bubble. The friction factor is equal to 16 by Re in this case, okay, low Reynolds number. Okay. And if you take also high Peclet number, okay, in the for this low Peclet number case, the correlation is going to be the same as the correlation for the flow past a particle. Sherwood number or Nusselt number is equal to 2. Okay. That is because in that case the flow does not matter, okay, it is only diffusion. So, for low Peclet number you get the same result for the gas bubble as you did for the solid particle. At low Reynolds number and high Peclet number, as we know, the correlation has to be independent of the Reynolds number, because for a laminar flow the flow pattern does not change, okay, the flow profile does not change as the Reynolds number changes in the limit of low Reynolds number, and therefore, all of the convective effects can be represented by the free stream velocity alone. Okay. And the Nusselt number or the Sherwood number correlation is equal to 0.652 Peclet number per half. Okay. So, that I can also write this as 0.652 Reynolds per half, Prandtl per half. Okay. Where the Peclet number, as I have defined it, is equal to V free stream times the diameter by the diffusion coefficient, or V free stream times the diameter by the thermal diffusion coefficient, depending upon whether it is a mass transfer problem or a heat transfer problem. Okay. So, this is the correlation for the low Reynolds number bubble. Okay. How about high Reynolds number? Okay, with the free stream velocity. You recall I had told you that if the interface is clean, there are no surfactants and so on, the interface is mobile, it is just an interface between a gas and a liquid with nothing that can cause rigidity at the surface. Once again, the velocity profile turns out to be symmetric, okay, between the upstream and the downstream sides. Okay. And at high Reynolds number, okay, the friction factor is equal to 48 by Re. Okay. So, we do not have the boundary layer separation, the wake formation, etc., for the flow around a bubble, okay, in general. Okay. So, the velocity profile is symmetric between the upstream and the downstream sides, and there is no boundary layer separation and so on. And in this case as well, you can get an analytical expression for the Nusselt number or the Sherwood number. Turns out that both of these are independent of the Reynolds number, okay, 1.13, okay, times Peclet number to the half, okay, where the Peclet number is once again V free stream into diameter divided by the diffusivity. Okay. So, in all of these cases, for the flow past a mobile surface, the correlation is proportional to Peclet number per half, okay, times a geometric factor sometimes, okay, times in some cases a geometric factor, okay, Peclet number to the half times a geometric factor. Okay. Note that when we had discussed the Colburn analogy, I had said that the Nusselt number by RE times PR per 1/3 is equal to only a function of RE. Okay. And I had told you that this applies only to rigid surfaces, and you see the example of that here. Okay. Correlations of this kind, okay, do not satisfy this, because if you divide by PR power 1/3, you do not get something that is only a function of RE. Okay. So, I will just warn you here that this Colburn analogy is not valid when you have motion past mobile surfaces. Okay. So, this completes our discussion of particles, bubbles and so on. Okay. Finally, I will discuss correlation for packed columns. Okay. A packed column is a column which consists of particles, and the fluid flows through the interstices between these particles, the interstitial spaces. Okay. With a free stream velocity Vfs, a length L, diameter d, and the particle has an equivalent diameter dE. Okay. Free stream velocity is the velocity in the absence of the particles. Okay. The characteristic velocity for flow through the bed is going to be equal to Vfs by epsilon, where epsilon is the porosity of the bed. Okay. Recall that we had derived the total surface area. Okay, which is equal to the number of particles times the surface area of each particle. Okay. The number of particles was equal to 1 minus V epsilon by Vp. Okay. I should change this here. V into 1 minus epsilon by Vp. Okay. V into epsilon is the porous area, the void space between the particles. V into 1 minus epsilon or V minus V epsilon is the volume of the particles, and divide that by the volume of one particle Vp, right. So, here Ap is equal to surface area of one particle, and Vp is equal to volume of one particle. Okay. So, therefore, the total surface area is equal to V into 1 minus epsilon Ap by Vp. Okay. And Ap by Vp is 6 divided by the equivalent diameter, because we know that Vp by Ap is equal to equivalent diameter by 6. Okay. So, this will be equal to into 6 by the equivalent diameter. Okay. And it is based upon this total surface area that the Nusselt number and the Sherwood number are defined. Okay. The Nusselt number is equal to Q average by 6 V into 1 minus epsilon by dE, and I am sorry, this is the transport rates. Okay. So, average flux is equal to transport rate divided by the total area. The area in this case is the sum of the surface areas of all of the particles, which is that the same as the surface area of the void space between the particles, okay, because surface area, the sum of the surface areas of all the particles is equal to the surface area of the void space between the particles. Okay. So, therefore, J average and Q average, the mass and heat flux are defined as the transport rate divided by V into 1 minus epsilon into 6 by dE. Okay. That is how you are defining the average fluxes, Q average and J average. Okay. So, for the flow through a packed bed, this is the definition of the average flux. Okay. And then the Nusselt and the Sherwood number are defined as Nusselt and Sherwood number are defined as Q average by K delta T into 1 minus epsilon by dE, okay, or delta C. Okay. These are defined based upon the equivalent diameter. Okay. So, recall that the void equivalent diameter, okay, is equal to epsilon dE by 1 minus epsilon. Okay. That is the void equivalent diameter. Okay. So, these things are defined based upon the void equivalent diameter. Note that I had said that the Nusselt and Sherwood number are non-dimensionalized by quantities which have terms which have the same dimension as the terms on the right side of Fourier's and Fick's law. That is K delta T divided by length scale, or in this case it should be D delta C divided by length scale, or D delta C divided by length scale. For the flow through the voids, the length scale is the void equivalent diameter. And we had derived earlier that the void equivalent diameter is equal to the particle equivalent diameter times epsilon by 1 minus epsilon. Okay. We had derived this when we discussed momentum transfer for a packed bed. Okay. So, therefore, these are defined as Q average by K delta T into 1 minus epsilon by epsilon dE, or J average by D delta C okay. So, those are the definitions of the Nusselt and Sherwood number, and the Reynolds number is defined the same way. Okay. The Reynolds number, as you recall, the Reynolds number for flow through packed beds is equal to rho V superficial velocity times the diameter of a particle by mu into 1 minus epsilon. Okay. And the correlations for the flow through a packed bed for the Nusselt and Sherwood number are typically of the form Nusselt or Sherwood number is equal to 0.5 Re per half plus 0.2 Re per 2/3 okay, times the Prandtl number or the Schmidt number per 1/3. Okay. So, these are very similar to correlations that we had for the flow through a pipe, okay, except that that factor of d by L that is there in a pipe flow is not present in this particular case, because this represents the flow through the voids between the particles, not the flow through an open pipe, for example. So, these are the kinds of correlations that you get for different configurations. I should emphasize at the end that these correlations are only representative, only indicative, they are not exhaustive. In specific domains, you will have specific correlations for situations in fixed parameter regimes, and you need to look in technical literature in order to determine the most appropriate correlation for your application. What I have done here is to familiarize you with the forms of the correlations that we get, why they have the forms that they do have, and how can we use these to do actual calculations. That has been the purpose of this discussion of correlations. Okay. With this, I complete the discussion on heat and mass transfer correlations around particles in pipes and in thin films and in packed columns. Next lecture, we will examine natural convection. I will continue this in the next lecture. I will see you then.